So let's go back to the exercise again. So we're doing question number 8, but let's go back to the question number 8 again, once again, and then we'll solve the couple of the other questions about this the gas reaction. Okay. So number 8. So the question was, I have CO and H2O. This was 1 mole and this is 1 mole. And then if I just allow them to do the chemical reaction, then this will produce CO, CO2, H2O, H2, and then also there will be very small amount of the oxygen. Okay. And at the 1500 degree Kelvin, okay, and we assume this is 1 atm pressure, total pressure. Okay, the question is, okay, if I start with the CO and H2 gas, and then if I mix it together, and there's chemical reaction between these two, and part of CO becomes CO2, and part of H2O become H2, and then during that also there's the small amount of oxygen can be formed simultaneously. And then my question is, what is partial pressure for each gas phases in the final state? So as I keep mentioning to you, there's always two kinds of questions. One is whether this reaction, which direction I'm moving now. So this direction. Then you have to calculate delta G. Okay, whether delta G is negative or positive or 0. That actually gives you the direction, okay? And then when you are asked actually now, what is the final state? It means we are assuming that this is equilibrium state. So it means in the final state, all the chemical reaction you can set up inside of the system, whatever it is, whatever the combination it is, that delta G should be 0. Delta G of reaction should be 0. That's the final equilibrium state, chemical equilibrium state, okay? So in this case, we don't care about how this is moving, but we want to know what's the final state itself, yeah? And the only reason why we actually give the 1 mole of CO and the 1 mole of H2 in the beginning is we want to make mass balance. Because at least we have to know what's the carbon amount, what's the oxygen amount, and what's the hydrogen amount in the final state here. So we cannot generate new actually additional mass in the actually during the chemical reaction. So that's the only reason we give the initial state. Okay? Or I could actually give it in the other way around. So, okay, let's assume I have 1 mole of CO2 and 1 mole of H2 mixing together in the final state. What will be my final gas composition? The result should be exactly the same. Or I say I have 1 mole of carbon, 1 mole of H2, and then 1 mole of the O2 mixing together at 1500 degrees Celsius. What will be my final gas phases? Assuming that all the carbon is reacting as gas and become gas phase. What will be my final state? Then it's exactly the same question. Okay? The mass input, the elemental actually the amount of each phase is exactly the same. Yeah? So, okay. So, this condition. So, whenever you have this kind of gas reaction or gas-solid reaction, even though, if you like, and whenever you want to actually find what's the final equilibrium composition, typically we write down kinds of the mass balance equation first. Okay? So, I have CO and H2O, and then some other possible phase is CO2 and H2, and then O2, for example. Okay? If you don't know some of the phase, and if you assume that is almost 0, you count it, but let's just put it all of them. Okay? All the possible phase we know, according to the actual question. Okay, this is initial state, and this is final state. So this is simply for the mass balance actually check, okay? And this is total. So total moles of the gas phase, and moles of CO, moles of H2, moles of CO2, and etc. So initially I have 1 mole and 1 mole. Okay? And according to the chemical reaction, because CO gas reacting with half mole of O2, and it becomes CO2. And then H2, half mole of O2, become H2O. So I have this delta G, not reaction 1, delta G, not reaction 2, at 1500 degree Kelvin. Let's assume I know this value, okay? Then, from this one, we know that CO will react probably with oxygen and become CO2. Okay, so if I assume I'm making certain amount of X moles of CO2, then the amount of CO will be in the end 1 minus X, because to make a mass balance for the carbon. Okay? And then H2O and H2. So if I start to making the H2 gas by dissociation of H2O, then let's assume that is Y, then this will be 1 minus Y. Okay? And then let's think about then oxygen in this case. So in this case, the oxygen amount will be, okay, so if I have this one become this one, I need minus X moles of O2 is removed from the system. And then if I have this reaction going to this way, then I'll have this moles of the oxygen will be generated. Is it okay? According to the mass balance again. And then the total gas phase, this is 2 moles. And then total gas phase here is, okay, 1 minus X, 1 minus Y, X plus Y. And if you do the all of this, so what's Y? 2 plus so this is total number of moles of the gas phase in the final state. Is it okay? So why I'm doing this one is, in some cases, if you want to, so in this case, basically, if you want to calculate partial pressure of the each phase, you have to know what's the total amount of the total moles of the gas phase. And then you have to divide this one by, you have to divide your each moles of the each gas species divided by total number of moles of gas species. That's a partial pressure, yeah? Wow. The mole fraction of the each gas phase, and then you have to multiply this one with the total pressure. So that's why, if you want to really do it correctly, you have to actually consider this one too. Okay? Now, under this condition, let's assume so two actually unknown value is X and Y. Okay? So in the last class, I just assumed that, okay, X and Y is very similar. And so we just used only one variable. Now actually make it really more actually rigorous actually way, then we have two variables. At this then it means I need a two equation, two independent equation to solve actually two independent variables, yeah? So what kind of equation I can think about? So one of the first equation, CO, oxygen, CO2. So at the final equilibrium state, this should be in equilibrium state too, yeah? This chemical reaction should be in equilibrium. You can take whatever chemical reaction you like. So this chemical reaction, or if you like CO plus H2O become CO2 plus H2, you can generate whatever it is. But this one is two independent equation. If you combine it together as one, that actually third equation is depending on these previous two, yeah? It's combination of previous two equations. So that's not independent equation, okay? So you have to combine it. You have to find out two independent equations, whatever you like. So this one or this one, two, this way. Or you can say, okay, this one, and then combination of this one together. That's another also independent equation if you like. Okay? Is it okay? So two variable, two independent equation we need. So let's assume I'll take CO, tap of the CO, CO2 this way. Then when the reaction one is in equilibrium state. So it means delta G of reaction 1 should be 0. Is It's delta G, not delta G naught, yeah? Delta G, okay? Reactant and the product at the solution state, that should be 0. Final state, that should be 0, the balance. Then, this will be delta G naught plus RT ln partial pressure of each gas phases. So partial pressure here, so CO2 X over this one, so X of 2 plus, so this is mole fraction of CO2 in the final state times P total, okay? And then CO is this one, 1 minus X over this one, 1 minus X over 2 plus Y minus X over the 2 times P total. And then O2, so O2 is this one, so Y minus X over 2 divided by Y minus X 2 plus so this is the inside of Rhone. Okay? It's much complex here if you want to really consider all of this. So this is one of equation. And then you have to be very careful. P total sometimes is very critical, okay? In this case, I assume 1 atm, so whatever it is, I mean just canceling out. But if the P total is not 1 atm, if it's 2 atm, this P total will contribute inside of this Rhone term. So you have to be very careful. It's not mole fraction. You have to consider P total always as a partial pressure, okay? That's very important. So, if P total equal to 1, so this is 1, and this is 1, and this is 1. So, to make a little bit simplify, this is actually the equation here. But anyway, this is one equation. And then, the second equation we can think about is, we can do the same thing for H2, H2O. Or, we can do a combination of this one. Okay, so if I do the same, so second equation as the second one as the other independent equation, then delta G2, so chemical reaction 2 is in equilibrium. If you want to set up in this way, this is same thing, delta G naught 2 plus RT, H2O, so 1 minus Y, and then this is Y, times also partial pressure H2O, so Y minus X over 2 okay, and then you have to solve the whole equation. So you have two independent equation, two variable. And delta G naught 1, delta G naught 2 is given in the equation here. In the question, sorry. So delta G naught 1 and 2 is given in the question. So you have two independent equation with two independent variable, but the variable looks very complex here. Is that okay? And if you're actually using the third one as independent equation, you can get a little bit simplified version. So for example, if you take a third one, then delta G not 3, and this third one is combination of 1 minus 2. Okay, so we can just cancelling out oxygen. Then at least y minus x over 2, this kind of term will be just eliminated here. Okay, you can make equation 1 and equation 2, and if you make 1 minus 2, and then if you take that as equation 3, so this means equation 3 is CO plus H2O okay? So I can generate another one. And in this case, if this is in equilibrium, then CO and H2. CO2 is, okay, X over total number of moles. I'm just saying total number of moles, and then P total, and then so total number of moles of gas is 2 plus y over x over the 2, yeah? Because it will be cancelled out, so I just make it very simply, just express it simply like this way. And then the other one, CH2 is x over, no, sorry, is it right? X, so H2 is x, and the CO2 is also, CO2 is x and H2 is y. Yeah, so y, number of moles gas, and P total. And then this one here is 1 minus x. Minus y, and this one is basically 2 plus y minus x over 2. Yeah, so that's total number of moles of gas. So, I mean, this case is, we are lucky. So all this one is eliminated. So it's much simplification, yeah. So this will be okay, and then you can solve if you like. Okay, but as I mentioned, I mean, one of the shortcut is assuming that oxygen is very small amount, because typically the amount of oxygen generated is very, because I know the more or less answer, just that's why. Then, or I can even give you, okay, it looks like, okay, you guys cannot figure out oxygen is very small, I mean, for example, under the very limited time constraint during your midterm, I'll give the hint, okay, assume in the beginning, oxygen is, or assume that oxygen is very small amount. Then you can assume that x and y, or the oxygen amount, so it means y minus x over the 2 is nearly 0. Then x and y is almost same. Then you can have the very simple equation. This will be only one equation you can just solve by basically, yeah. Then you can get the x value, and then you can enter that x value, and then do all the thermodynamic calculation again to find out what's the oxygen amount, and then prove that that oxygen is very small amount. Then it's valid assumption, yeah. Okay, that's another way. Okay, so this is, so either you take either 1, 2, 3. Among 3 of these, you can take at least 2 independent equations to solve x and y, or shortcut is assume PO2 is nearly 0, then it means x is nearly same as y, and then you get what's the X value, and then once you get, you enter it again to the either question number or reaction 1 or reaction 2, and then you get what's the real oxygen partial pressure. Okay, and then either 1 or 2, then you take what's the partial pressure of the O2 again. Okay, so this is another way. But for this one, you have to make sure that PO2 is really small in the end to verify your assumption. Okay? So if you have the good computer, you can just use the first method. But if you don't have actually good computer and if you have very, very, very stressful under the constrained time, if I give you some hint, you can take this way. Okay? Good. So this is most important step. This is most important step. Okay? When you also take this one, you have to be very careful because I actually checked the graduate student this year, and they took actually all this so-called preliminary exam or the qualifying exam for the graduate student. And then I asked not as complex like this one, more simple one with a solid phase together. And then they will start to writing all this kind of equation. And the question was not really for this kind of thing. But anyway, they tried to set up some mass balance equation like this. And then they were even counting solid phase as a total moles of the gas phase. And then when they actually calculate partial pressure, they are counting wrong value because there was some solid, there was some gas. And they count solid into the gas, total number of moles of the gas phase together, and then calculate partial pressure. That's wrong. Completely wrong. Okay? So when you see later, when you have some kind of question which say, okay, there's still certain amount of solid is remaining, that solid should not be taken into account this total number of moles of the gas phase. Okay? In the calculation for the partial pressure. Okay? Very good? I warned you already. Okay? Okay, question number 9. And also R is always 8.314 when you're using the joule, yeah? And when you use the ideal gas law, it's 0.0083812. Okay? Don't mix it. And temperature in the thermodynamic calculation, if it is not specified, it's always in Kelvin. Okay? I'll really check how many of you make a mistake for these 3 in your midterm exam. Okay? If you are doing homework by yourself, I'm pretty sure you have no problem. If you start to copying the actual homework from the other student, you'll end up this kind of very, very simple actual mistake. Okay? Do the collaboration for your homework, but in the end, you have to actually try to write down by yourself. Okay? You cannot get the answer in the most of this question. You cannot get the exactly same answer up to the last 3 digits. It's almost impossible because you make something, some assumption, some value taken from some previous, the step. Then you always end up slightly different answer. Okay, that slightly different answer is more correct. Then make exactly the same answer. Then it means you copied you're copying actually your homework from the other student. Don't do that. If you do that, not only for you who is copying the homework, the student who actually show you the actual homework have the same problems. I'm trouble with you together because of you. Okay, so do it yourself in the final state. Okay, but I'm still really encouraging you to work together. Okay, question number 9. So we have the container with the volume of the 100 liter. So that L looks like 1 or I, but that's actually liter. So we have 100 liter container. And then we are charging 0.1 mole of H2S gas and 0.1 mole of H2 gas inside of this container. So volume is fixed, volume is not expanding, volume is fixed, and we are adding this kind of the gas phase. And the container is sealed and heated to the 1000 degrees Celsius. Okay, calculate pH2S, pH2, and the PS2. So it means, okay, I'm adding H2S and H2, and there's additional gas, S2 is forming here. So it means there's some chemical reaction in between three, then make S2 gas, okay? And then we have to find out what's the partial pressure of the three gas phases. So this is also final equilibrium state calculation, yeah? So we can do the exactly same kind of we can apply the same kind of method as the previous question. So I have a container which is 100 liter, okay? And I'm adding H2 and 2S. Is 0.1 mole and 0.1 mole. Okay, I'm making chemical equilibrium in the final state at 1000 degrees Celsius. So it's 100 liter and then 1273 Kelvin, 1000 degrees Celsius, and this will form H2, H2S, and S2 gas, all three gas. What's the partial pressure of each of the three? So, same thing, we do the mass balance equation first. So I have H2, H2S, S2, and total. So this is number of moles of each phase. So here initial, final state. So H2 0.1 mole and 0.1 mole, and total was 0.2 moles in the beginning. And then final state, this is, for example, H2, the chemical reaction is H2S. So delta G naught is given at 1000 degrees Celsius. So this is chemical reaction, yeah? Okay, so it means, okay, H2S gas can dissociate, yeah? So 0.1 minus X, and H2 is then half of X. If you like in this way. And this one is it okay? You good? Then the total is 0.22 plus 0.5x mole of gas can be formed in the end. You good? So the only actual chemical reaction we can consider is this H2S dissociation reaction. So at equilibrium state, in the final state, so this reaction should be in equilibrium internally in this final state here. Then delta G equal to delta G naught plus RT ln. Now partial pressure. So H2 0.1 plus X over total 0.2 plus 0.5x, and then I have P total because I don't know the P total yet, and then S2 okay, So in root, it's a half mole. And then H2S. So I have to solve this one. And this is 0. That's good. And this value is given. And T 1273 Kelvin, R 8.314. So there's only one, actually there's two variables, X and the P total. P total is not actually, so this one eliminate together. But this inside, we have root of P total existing. So there's two variables. Okay, so we have to find another equation to define what's the P total, yeah? Right? So that's the actual reason why we actually have this one, 100 liter. So PV equal to nRT, ideal gas law. Yeah? So we have P total, V total equal to N total, R, T. Right? So now you have two different R in the same question. That's why you have to be very, very, very careful. Okay? So ideal gas law R, and then delta G reaction R is different R, yeah, R value, different unit. Okay? So when you use the 0.082, sorry, yeah, and then N total, so P total equal to N total, so N total, this is N total, yeah, final gas amount, number moles of the final gas, 0.2 plus 0.5 X, and then V total, so V times R T. So you can actually, so this is 100. So this equation here is going to the inside of here. So another X variable here. Okay? It's a little bit complex, yeah? I mean, definitely I don't think you can calculate by hand. Okay? Good. Question 11. So now we have the pure oxygen is injected into the bottom of the coke heated at 1600 degrees Celsius. When equilibrium is reached, the gas phase is become CO, CO2, and O2, and the total pressure equal to 1 atm. And this is the equilibrium with the coke. Okay, so equilibrium with the coke, it means okay, coke is still there. Yeah, equilibrium with the coke. So coke is not consumed completely. There's still coke remaining in the inside of this actually bottom of the some container. And then calculate CO, CO2, and the PO2 at equilibrium state. Okay, so it's basically, so this is 11. This is no actually realistic actually question. And it's actually happening like this. So inside of, some reactor, we have coke. Coke is basically carbon. Okay? Coal is, so when you actually have the coal, when you burn it to remove some impurity, it becomes almost 99% of the carbon. That's we call it as coke. So when you go to the steel making plant, I don't know whether you learned actually iron making and steel making. So we are adding coke with the iron oxide together to make iron metal, yeah? So that's coke. So charcoal, and then if you burn it, it becomes coke. So when you actually burn the, for example, more or less like when you have the wood, and then when you actually burn it, if you make a, we call it like soot, yeah, soot in Korean, and that actually is almost close to the coke. Okay, so it's a pure carbon, active carbon source for the chemical reaction. Okay, and then now I'm injecting here oxygen gas. Then this one and this one reactor, and they produce lots of CO gas phase. Okay, in iron making, that actually CO gas is really reacting with the iron oxide. So gas solid reaction. It's not solid reaction. Solid reaction is much slower because solid reaction is only happening at the solid interface here. But when you make a gas phase, gas can go to the all around the porosity and pore between the ore, and then it has more fast chemical reaction. So we want to actually make CO gas phase here, and it will produce CO2, and then certain amount of oxygen. So I want to calculate what's this one at 600 degrees Celsius. Okay? And at least we know that this total pressure 1 atm. Okay. So the chemical reaction we have is carbon. So this is solid, and of course this should be gas. And then we have the other one. So we have these two reactions. So carbon is solid. Okay? So at equilibrium state, okay, so if I know this one, if I assume this one, for example, this is in equilibrium state inside of this furnace, then this is existing, so equilibrium, this is still existing in the equilibrium state. So I know two variables here. And according to this one, I know two variables here. And one of the variables is same. So I have two equations with basically two variables. Or I have 1, 2, 3 variables. However, one of them is eliminated because if you sum up together, it should be total pressure equal to 1. Okay? So I have 1, 2, 3 equation. Is it okay? That's what we have to do. Okay. So let's take it this way. So then so at equilibrium state, okay, so you can have delta G of reaction 1 equal to 0, and this is delta G not of reaction 1 equal to, so let's do slightly different way. So PCO, and then solid, so activity of carbon solid, and PO2, this is 1, okay, and the other equation, and this is 0 at equilibrium state. Same thing. Okay, so we have another equation. So 1, 2, 3 variable, and then we have PCO, and this is total pressure. So we have 3 equations. Okay, I'm not using initial and the final, yeah. So, I mean, you can set up in that way, initial and the final, but there's no point here So that's why I just go directly in this way. And of course, you can eliminate, combine these two together and eliminate carbon. Then you can set up internal gas equilibrium. CO2 becomes CO2. Yeah. That also can be actually checked if you like. Okay? Good. Number 14. This is so simple. I mean, calculating delta G at the given temperature. I mean, you have H298, S298, and then you have heat capacity. I mean, this is what you have done basically for your homework number 1. So, this is not necessary. Question number 17. I like this kind of question. And if you look at all the past midterm, at least every 2 years or almost every year, you see actually this kind of question. Because this requires a little bit more thinking, you know. It's not just one calculation. You have to do multiple calculation, and then it requires your judgment in the end. I guess it's a little bit, you have to think a little bit more. Okay, so we have a hematite. Fe2O3 is hematite. Do you know, by the way, different iron oxide name? Name of the different iron oxide? So we have, depending on the partial pressure, so we have iron. If you oxidize this one a little bit more, it becomes iron oxide, FeO11. It will change it in this way. At least if you're coming, I mean, if you graduate from metallurgical engineering, typically at least you have to know this one. And now it's material engineering or material science and engineering, but one of the most common material we actually dealing is the iron, because steel is one of the most common actually the metallic, you know, material we are using. So at least you have to know a little bit about this naming. Okay. So here we call this one, of course, iron. Okay. Do you know, by the way, what's the difference between iron and the steel? Iron and the steel? Have you heard about like a little bit how we actually distinguish iron and the steel from your material introductory course? You never heard about this one? Iron and the steel. Carbon inside of iron is called steel. 50%. Why only carbon? I mean, carbon could be almost zero, yeah? So typically when you say carbon and iron, sorry, carbon. When I typically say, okay, the steel and the iron, because I mean, you probably heard about cast iron, and which contain typically about 4% of the carbon, okay, cast iron. So typically when you say, I mean, in terms of the steel making process or iron and steel making process, when you first produce the steel or iron by the iron ore reduction by the carbon or CO gas, it will produce the liquid iron containing about 4 or 5% of the carbon. That we call it typically iron or pig iron, P-I-G, pig, really. The pig, animal, pig iron. I don't know whether you heard about this one or not, but we call it pig iron. And then by adding oxygen into the steel, carbon oxygen react together becomes CO gas or CO2 gas. In that way, carbon can be reduced to the certain minimum range or certain range which we want to actually produce as a final product. Then we call that actually state as steel. That's actually okay. According to the steel making process, we define in this way: iron and the steel. Steel is controlled composition kind of product, and the iron is just uncontrolled composition product. So that's actually more correct way to say. Okay. So steel is typically when you actually change the impurity and alloying it, and then make a reasonable final, you know, the final product with a controlled composition, that we call it steel. And then if you just produce it without any control, that's iron, typically. Okay? So Fe is ion. You know BCC, FCC, and BCC transformation of the ion, yeah? So we have ion transforming from BCC to the FCC at around 900 degrees Celsius. That's first transformation. And then if it heat up to about 1400 degrees Celsius, FCC become BCC again. And if you heat it up further, BCC become liquid ion at around 1550 degrees Celsius. Okay? So BCC, FCC, BCC. Okay? And when ion is BCC state, below about 500 degrees Celsius, we have ion, BCC have magnetic property. Okay? So when you actually put the magnet, stick together in the BCC state, not in FCC state. Okay? And this one, when you actually make oxidizing of the ion, the first ion oxide, we call it this one as Hematite. And this is the German name, Hematite. Okay? And then when you make a little bit more oxidation, so this is ion 2 plus, and this one is ion 3 plus state. Yeah, more oxidizing condition. And in the middle, this one have ion 2 plus state and 3 plus state together. Fe3O4, you have, so 4, so you have 8 anion, 8 electron, and then you need 8. So Fe3O4 is 1 mole of ion 2 plus, 2 moles of ion 3 plus inside of Fe3O4. We call this one magnetite. Yeah, magnetite. And why we call it magnetite? It's a magnetic. It's very simple. Magnetite. So at the low temperature, about 700 degrees or below, this is actually have the magnetic property. Okay? And then this one, we call it hematite. Okay? So most of the ore we are getting from the natural state is the hematite, most oxidizing condition. Okay? And then if you actually reduce this one by the CO gas, then it becomes Fe3O4, and it becomes FeO, and it becomes ion. Just step by step, it's moving this direction. Okay? This is necessary here. That's why I'm explaining to you. Okay, so let's go back to our question. Okay. So question number 17. So we want to actually reduce the mineral Fe2O3 with hydrogen, okay, at 1000 degrees Celsius, okay. And the operation condition of the furnace is pH2H2O. We are controlling this H2H2O ratio in the furnace. So gas, partial pressure of H2 and H2O as a 1-to-1 ratio at 1000 degrees Celsius. What is going to be produced in the final state? Okay. So if you have only one product, it's very simple. Then we can just look at that actual chemical reaction and see whether that delta G of that reaction is negative or positive. If it's negative, it means that product is produced under that H2H2O condition. Yeah? You understand what I mean? So it's almost same as our very first question. Okay? So you have nickel and nickel oxide. Well, you have nickel, and then I have this partial pressure of oxygen condition, COCO2. Okay, is this nickel will become nickel oxide or nickel metal? Yeah? So, I have gas and then metal. Under the gas condition, there will be certain partial pressure of oxygen, and that actually make a reaction with this one, and then make a chemical reaction. Is that going to be forward reaction or backward reaction? Yeah. So I'm asking you, what's not final state? I'm asking you whether this reaction going to the forward or backward. Okay. So I have this gas condition. If I add this Fe3O4, so this one is number 17. I'm having Fe2O3, sorry. I have H2O gas inside here. and this H2H2O gas one-to-one ratio. Is this one going to stay as it is, or is it going to change to the Fe3O4, or is it going to change as FeO, or is it going to change as ion? So this one. So I have here in this state, is it going to be ended up this one, or is it going to be ended up this one, or is it going to end up this one? That's my question. Okay? So we have to calculate delta G of reaction, basically. Yeah? Okay, so let's look at one by one. So if you look at Fe oxygen, so we have, so the reaction 1 is Fe. Second one is last one is okay. So we have this. So we know all the delta G of each of this delta G naught for each of this chemical reaction. Okay. So let's think about, okay, so I have initially Fe2O3. So I have to start from Fe2O3. That's the very first condition, yeah. So the very first one you can think about, the third one. Okay? So I have Fe3O4, Fe2O3, and then this one. And I have to know the partial pressure of O2 under this condition, yeah? But if you look at the question number, the equation number 4, O2 is controlled by H2 and H2O, yeah? Okay? So first test, okay, let's assume Fe2O3 going to the Fe3O4 or not. So this one, is it going to be possible or not? So we are starting from here. So by combining 3 and 4, we can eliminate oxygen, and we can get only H2, H2O, and Fe3O4 and Fe2O3 relationship, yeah? So by combining 3 minus 4, then we can have 2 Fe3O4 plus H2O equal to 3 Fe2O3 plus H2. And of course this is gas phase, and this is solid and solid. Each solid is stoichiometric solid, not solution. Okay? So I set up this chemical reaction. So and this one, delta G not 3 minus delta G not 4 for this chemical reaction, yeah? So delta G of this reaction, because I'm checking whether it's going forward or backward, yeah? So delta G of this reaction equal to delta G naught of the 3 minus delta G naught of the 4 plus RT ln under my current condition. Okay? So activity, this one is 1, and so this is partial pressure of H2, and then this is 1, so this will be partial pressure of H2O. Is it okay? Eventually. The activity for both solid is 1. Do you follow it? Okay? Then this one is 1, yeah? That's what is given. So this term is 0 basically. Inside is 0. Okay? So this is same as this one. 3 minus 4. So if you look at 3 and the 4. 3 is minus 68494, and then 4 is minus 178128. So 3 minus 4 will be positive, isn't it? 3 minus 4 should be positive term. 1, 2, 3, 2, 6, 2, so 5. Yeah. Am I right? So this will be positive. So it means what? I am having backward reaction. But the value, let's look at the value. Because I'm specifically showing you the value because you're going to make a problem later if you're just looking at the value. So 3 minus 4 is, okay, here minus 6, 8, 4, 9, 4 joule. And then this is minus 1, 7, 8, 1, 2, 8. So this minus this. So it's 10,000 or 109,000. 634. It's a huge number, positive. And this means I'm going to the backward reaction. It means if you look at the chemical reaction, backward reaction, okay, Fe2O3 will become Fe3O4. Am I right? So this will produce, so Fe3O4 will form. Okay? Now, let's look at, so is this the end? No. We have to check one by one, everything. Okay? So now, okay, Fe3O4 is done. How about, it can also make FeO, yeah? We have to check the FeO. Okay? So, you can combine this and this together, these three together. Okay? And Fe2O3 and all this combination, you can make FeO too, yeah? So, if I make 2 times of this one, and minus this one, or 2 times of this one, plus this one, and minus this one, then Fe3O4 will be eliminated in the middle, and then it will become FeO plus, so this one is FeO3 FeO plus half mole of O2, or the 3 moles, 6 moles of FeO plus 1.5 moles of O2 will become, Fe2O3 and the H2 and H2O, something like this, yeah. But unfortunately, the oxygen is still inside in the system, so it's not very good. So, do we have to really check, okay, from Fe2O3 or not? This is one of the questions you can think about too. Okay, so we are looking for, okay, whether this one will become this one become this one, or this one become this one. Okay, so this will become this one. And then I check this between these two now. Is this one become this one? If it's not, then this one is more stable than this one, yeah? And then we can check with this one and this one. Is it going to be, this one can be changed this one or not? Because we know at least this is forming from Fe2O3. So I don't have to start with this one anymore. Because consider this condition. This is changing to this one. So I know intermediate state or final state. I don't know whether it's final or not, but this is forming under this condition. And then if I assume that, okay, if this is forming, is this going to form or not? Is it okay? We can do it in this way too. So we check, okay, whether this is forming or not. Okay. Okay, second step. So how about between Fe3O4 to FeO? Is it going to form or not? So, if you look at actually this one, then, okay. I have Fe3O4 and FeO, this chemical reaction here, reaction 2. I can combine reaction 2 and reaction 4 together. 2 and 4 together. So 2 minus 4 will be FeO H2O Yep. And this delta G naught two. Okay. So at this condition, delta G of reaction is delta G naught plus again pH2 pH2O. Am I right? Okay. So this will be, so this is eliminated again as 1. And then delta G naught in this case is 2 minus 4. So 2 is minus 1, 3, 8, 1, 3, 0. So this will be this minus 2 minus 4. So 3, 9, 9, 9, 8. So it's a positive. So it means I'll have backward reaction. Yeah. Delta G will tell you what's the direction of reaction. I'll have backward reaction. Backward reaction means Fe3O4 become FeO. So this is stable. Yeah. So FeO will form. Is it okay? So this one means yeah. Now, okay, so we check, okay, this one could become this one under this condition. And then we saw this is the final state, but this one can become this one now. So it means this one can become this one, yeah? Step by step up to here. And then is this going to be this one or not? Let's check. So that one, we can use the equation 1, yeah? 1 and the 4 again. So this is okay. So 1 minus 4. So as you can see, 1 minus 4 looks like negative term already. Yeah? So 1 is minus 1, 8, 9, 7, 7, 6. So minus 1, 1, 6, 4, 8. So it's a negative. So it means the chemical reaction going to the forward reaction. So it means Fe will become FeO. Yeah. Do you understand? So if you go step by step like this, you see that, okay, so when you have the series of this kind of the oxide form, then you have to check one by one. But you can check from the very beginning to the each. So this one to this one, this one to this one, this one to this one. This is one way, but that is not actually very accurate way. I'll show you now why it's not accurate way. But the most accurate way is really going to the one and then check, okay, this is stable. And then how about that stable one to the next one? Is it going to stable or not? And then if this is forming, then this one will check with the remaining one. Because this is, if you check this one, definitely this will be formed because this is already formed from here, yeah? So this will be always like this, but next one, okay? And so you have to check one by one, and then in the end, okay, so this is most stable one. This is most accurate way. Okay, one of the methods, but this is most accurate way. But now let's take it in this way, as I told you. Okay, how about this one to this one, this one to this one, this one to this one? What will happen? Okay, so let's assume this one become this one. Fe2O3 become FeO. Okay, so now I'll show you wrong one. Okay, you should not follow this way. I'm showing you wrong calculation. Okay, so Fe2O3, FeO. So how can you do that? So Fe2O3 become FeO. So I have to combine these two together, yeah? Okay, and so I have to combine these three together to make this chemical reaction. Okay, or one of the ways, okay, so in the very first one, I have this combination equation. 3Fe3O4 plus this one is this one. And then question number 2 was this one. So if I mix the first one, so first one, that was 3 moles of Fe2O3 and 2 moles of Fe2O3, and then plus 2 of the reaction 2. So this one. Is okay? So if I take 2 times of this one, and then 1 time of this one, so this is 1 time, so let's assume this is this one, let's assume this is this one. If I take 1 and the 2, yeah, then you can eliminate everything, and then you can get only FeO and Fe2O3 relationship. Then this will give you, so 1, 3 Fe2O3, and then H2, and then H2O, and then this one, 2 moles of this one, so 2 moles of this one, 2, 2, so this will be 3, and then 2, so this will be 3, plus 1 more, 3, no, 2 more, 3, and then this is then 6 moles. It makes sense? Is it okay? The mass balance is okay? Yep. So then delta G of this reaction is delta G naught plus RT ln. Eventually, it will be same. So everything will be eliminated, and the pH2 and pH2O Q, and so it's 0, yeah? Or 1. So entire this term will be 0, yeah? So delta G is only delta G naught. So delta G naught of this one is 1 time over the 1 and 2 time over the other 2. So this one, 2 times of this one, and then 1 times of this one. Yeah. So this will be this plus 2 times of this one. So 149632. Is it okay? 1 plus 1? 1 plus 2. 2 times. Why is it not working? 2, okay. So 189630. Is it okay? And then let's look at another equation. Let's just delete this one here. So that means this is very positive. So according to this one, what will happen? This one going to this direction, and FeO will be formed there. So is it okay? According to this one. And then, now how about Fe2O3 become Fe metal directly? Okay, so now we have to combine all these equation, and then Fe so this one, okay? So this will be Fe so in making mass balance, 2 moles of Fe, 3 moles of oxygen. So 3 moles of oxygen. Yeah, okay? This makes sense? This makes. So, in order to generate this one, according to your chemical reaction here, so if I combine all this one, so 1 minus, how do you do it? So 3 times of 1, probably I have to do this one. So 3 times of the number 1 reaction plus 1 time of the number 2 reaction, and then it will form FeO, and then FeO, Fe3O4, Fe3O4 will be, so this is 2 times. This will be 2 times. This is 6 times. And then last one, 1 time of number 3 plus then 2 times, am I right? So 3, so 2 last one is 1 time, 2 times, okay, then it eliminates 6 and 6 times, yeah, and then 9 times. 9 times of the number 4. Okay? And this will make actually, so this will be 2, 9 times? Minus 9 times. So this will be then, so third one, 3Fe2O3, yes, 3Fe2O3, and then 9 H2, and then 3, 6, 9. Is it okay? So if you do this one, you can get this chemical reaction. And delta G of this reaction, the same thing, delta G naught plus RT ln partial pressure = 9, yeah. So delta G of reaction here. So 6 times of first one. Plus 2 times of second one. 반대로 돌리면 되니까. Sorry, I'll do that later. And then third one minus 9 times of the last one. Yeah. So 119742. So according to this way, am I right? Is it minus? This is Fe2O3, and then this is minus here. Minus, 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 plus. This is okay? Okay? Sorry about it. And this will be minus. You good? To make this chemical reaction. Okay? Joule. It's negative. It's negative here. So it means forward reaction. So I'm going to the forward reaction. It means Fe2O3 become Fe metal. Fe metal will form. What the heck? I mean, Fe3O4 is from Fe. So look at this. According to this one, from the Fe2O3, so we start from Fe2O3. Fe2O3 will form Fe3O4. That's the very first one. And then instead of doing this one, if you start from Fe2O3 again, forming FeO, okay, FeO will be formed. And then, if you're doing this one, Fe will be formed. So all three can be formed. Then how can I tell which one is really formed? Is it all three formed? No. One of this one will form. Not all three. Big question mark. Then, okay, let's look at the real value then, okay. So, look at this way. 2 moles of Fe, so this is 2 moles of Fe2O3 become this way. 3 moles of Fe2O3 this way, yeah? Okay, so this is 1096, or 109, for example, kilojoule, with 3. So if it's divided by 3 moles into the 1 mole, if you make it 1 mole base, then this will be this one divided by, for example, okay, so it's about 36 kilojoule per mole of Fe2O3. Okay, and then let's look at this one. Okay, this is now 3 moles, so I divide by 3 again. So this divided by 3, so it's about, so 3 is like about 50 or 60, yeah? 60 kilojoule, am I right? And then this one, okay, now I have 2 moles, 3 moles of this one. Again, I divide this one, so it will be about 20 kilojoule, or no, 40 kilojoule. So, does that dictate, okay, this is really formed? No. You should not do that. That energy difference doesn't give you really whether this is really stable or not. It's a bit dangerous. Okay? we are just doing the transient calculation. It's not final equilibrium state. If it's final equilibrium state, then yes, lowest energy state is the one we want to produce. But we don't know whether this is lowest energy state. Now we are just start to doing the chemical reaction. We are still in the middle of the chemical reaction. So we cannot really say this is most stable state according to the energy itself. Okay? So the only way is, you do, if you like, you do all this one, so long way, and then you see that, okay, all three can be formed. Now between these, which one will be formed? You have to combine it again between the product, all three possible product. Then you have to go back again to the second step and third step I showed you before. Okay? So the most easiest way is you start from the actually first material you have in the question, and then you actually do the calculation for the second one, and then okay, the second one will form or not. If it's not formed, forget about it, and you start from the original one, and then test the other one. Is it form? Okay, it's a form. Okay, then let's take that one as a now starting material, and then check with the other one. Is it going to form or not form? So you have to go step by step with all the possible intermediate phase. That's the most safest way, most shortest way actually. Otherwise, you have to do all this one, and then you have to think about, okay, so between this you have to do it again and again. Is that okay? This is one way. I'll show you the other way in the next class. Any question?